Hello and welcome. My name is Ricardo Lewis. I'll be covering section 2.5, the eye, and 2.6, the camera. Section 2.5 is about the eye and the physics behind it. This section is good because I've always wondered how the human eye works. Also, because I have a close relationship with my glasses, and I found it impossible to figure out how the eye processes images. Section 2.6 is about the camera and the physics behind it. This section is good because I have always wanted to learn how to properly use a camera and what the physics were behind it in relationship to our eyes. To further our understanding of the eye, we will look at the physics of the eye. In this slide, you'll see how the human eye processes images. There are many different parts that are in the eye, but we will focus on the basics of the eye. On this slide, you can see a basic anatomy of an eye. The cornea and the lens of the eye act together to form a real image. On the light-sensing retina, which has the densest concentration of receptors, is the fovea, and a blind spot over the optic nerve. The radius of the curvature of the lens of an eye is adjustable to form an image on the retina for different object distances. The pupil is the hole in the eye that allows light to reach the retina. The pupil widens in a darker room to allow more light in, and narrows when the light to restrict the amount of light to reach the retina. The pupil is adjusted by the iris muscles. The lens is located in front of the iris. It is an elastic body. It stretches and returns to its former place. It is a biconvex and almost transparent. Directly in front of the lens is the aqueous, and directly behind it is the vitreous. The lens is one of the items in a person's body that deteriorates with age, like many other body parts. The lens will lose its elasticity, which reduces the ability for it to change shape easily and result in a person needing a type of aid for nearby objects, often in the form of reading glasses. The purpose of the lens is to refract light that enters the eye through the pupil and gives the ability to focus on the retina. The lens also contains the ability to absorb ultraviolet radiation and is thus kept from reaching the retina. This absorption of ultraviolet radiation is actually what leads to cataracts. A lack of transparency of the lens, usually found in older people. So the retina, the center of the eye, is more in more than one ways. So cells in the retina break down what a person sees in thousands of elements, such as brightness, color, movement, etc. The job doesn't stop there. However, it also tells the brain these things through electrical signals. This is done very quickly, more quickly than humans can understand, even with highly sophisticated help. Layers of rods and cones receive light. Then bipolar cells organize this information and send it to particular cells, which then send it to the brain via the optic nerve. On this slide, you can see that in the human eye, an image forms on the retina. Rays from the top and bottom of the object are traced to show how a real inverted image is produced on the retina. The distance to the object is not to scale. So this means the cornea and lens can be treated as a single thin lens, even though the light rays pass through several layers of material such as cornea, aqueous humor, several layers in the lens, and the vitreous humor, changing direction at each interface. The image formed is much like the one produced by a single convex lens, which is a real or inverted form of what we actually see before it is processed in a sense. So although images are formed in the eye are inverted, the brain inverts them once more to make them seem upright. On this slide, we will look at an example. The example is finding the effective focal length of the eye. An example of finding out the effective focal length of the eye is to note the difference about the eye, and that is that the object moves and the retina cannot. The image must always appear clearly on the retina as the principal focal point changes. This is carried out by the eye changing the thickness of the lens, unlike a camera, according to whether there is a near or far object. The nearest human eye can focus on an object 25 or 250 millimeters away uh, from the front of the lens, and the furthest is to infinity. As seen on this slide, there are many ways you can use this formula. In the basic form, you can determine the principal focal length of the eye to the nearest point. The other variation is to determine the furthest at infinity with the 1 over dO, which is the object distance being changed to infinity. On this slide, we'll look at vision correction. I want you to note two reasons that plague the majority of those who wear glasses or contacts. And that's due to either nearsightedness, which is called myopia, or farsightedness, which is called hyperopia. These are typical vision defects as seen in this slide with geometric optics, where some are simple and are able to be corrected. Taking a deeper look, we will note nearsightedness, which is myopia. It means that a person is short-sighted. That's a person's sight that is good at short distances. As seen on the previous slide in the A part, this is caused when an eyeball grows too long or the cornea becomes too steeply curved and light rays focus too far in front of the retina. The retina only receives a blurry image. Now, in order to correct this, the best way to get the image to focus is to use a concave lens in front of the convex eye lens using the same formula mentioned in slide 4. In this correction, the eye focuses in on the image distance, which is di, that is subtracted from whatever the corrective lens is fixed at in centimeters away from the eye, which in turn focuses on the retina. Next, we will look at farsightedness on this slide, which is hyperopia. That means a person can see things clearly in the distance. Again, as seen on the slide in the previous slide 4 part, in this B area on slide 4, this is caused by the eye being too short, the cornea being too flat, or the power to focus being too weak, and the light focuses too far behind the retina. So this causes the retina only to receive a blurred image as well. Now, to correct this, the best way to get the image to focus is to use a convex lens in front of a convex eye lens, which is our natural eyes, using the same formula mentioned in slide 4. In this correction, the focus is on the image distance that is subtracted from whatever the corrective lens is fixed to in centimeters, and again it's subtracted from the object distance so that the eye and each area is on the same level, which in turn focuses the retina. Now we will look at 2.6, the camera. Cameras have been a popular device ever since they were invented during the late 1800s. Cameras are the electronic eyes that give us the ability to capture a moment with the push of a button. These little machines allow a real-life image to be seen on paper and to be kept as a memento. The way that cameras are able to do this is through physics. Cameras are relatable to physics because they involve visible light refraction, light reflections, and electromagnetic fields in the motor or the sensor, the CCD, which is the charge coupled device. Cameras are involved with physics because they use visible light to capture a picture. Visible light is part of the electromagnetic spectrum. The electromagnetic spectrum contains different wavelengths of frequencies. The visible light spectrum is part of the electromagnetic spectrum that humans can see. Specific wavelengths in the spectrum are represented by specific colors. This is how humans are able to perceive colors, through visible light. When a camera captures an image, it uses visible light to capture different wavelengths. These wavelengths are seen as different colors which come together to create the image. Visible light is what allows the colors that create the image to be seen when the picture is captured. Now, initially, photographs were recorded by using the light-sensitive reaction of a silver-based compound such as silver chloride or silver bromide. Silver-based photographic paper was in common use until the rise of digital photography in the 1980s, which is intimately connected to the CCD, which is the charge coupled device detectors found in cameras. On this slide, you can see how, in connection with its original counterpart, the eye, the camera works in a very similar manner to an eye. The light passes through the lens, which is refracted through the flip-up mirror and will pass through the viewing system, continuing to form an image upside down on the charge coupled device CCD detectors on the camera, just as an upside down image is formed on the retina in the back of the eye. Now, we can use the lens equation, as you can see on the right side of this slide. By the way, is a scary equation. Now, to determine the distance that is fixed from the lens of the camera to the CCD detector, you can utilize the I/F equals I/do plus I/di, which reads if I do, I die formula to determine that distance. Thank you for taking your time to view my presentation. Have a wonderful day.